Hi. Composite objects are basically rigid bodies or objects that are made up of more than one part. So we can think about bars and discs and blocks, but we can also connect those two, maybe rigidly, and then look at the response of that new composite structure. I'm Dane Quinn from the University of Akron, and today I'd like to give you a video lecture that deals with these composite objects and also sort of highlights linearization as well. Here's the system that we want to look at. Notice over here on the right, I have a composite object, right? So I have a disk, mass m2, radius r, that is welded to the end of a bar of mass m1 and length l. Again, the fact that these are welded is important. So this really acts as a single object. To this object, I attach a spring, stiffness K, a third of the way down the bar, and a damper with damping coefficient B, 2/3 of the way down the bar. Here, I've kind of tried to indicate that this spring and damper remain vertical as the bar moves. Ultimately, I'm going to linearize the equations of motion here. So when I do that, it actually is the same if I were to rigidly fix the end of this spring to the ground and this damper so that they started off in the vertical position. Right? But as we go along with the modeling, we'll kind of see where that comes in. So one important thing here is that I'm going to assume that the system is in static equilibrium when the bar is horizontal. Right? So if everything is sort of lined up here, then the bar is in its static equilibrium position. And at the end of this, we'll talk a little bit more about that, because what that does is allows us to neglect the role of gravity, as well as the unstretched length of the spring and the static displacement that comes along with that. So, how do we start? Well, we think about the objects and the motion and the forces. We think about the response of the system. Well, so the object here is this pendulum. Right? So we'll call it beta is pinned at this point in the ground, right? So that'll be O. So it's pinned at O and rotates. Now, only one coordinate is needed to specify where this object is. So it's a single degree of freedom system. Again, we only need one coordinate. However, we'll actually identify several in order to help us along with the modeling. And the reason that we'll identify multiple coordinates is because not only are we interested in the rotation, but we'll need to calculate the stretch in this spring as well as the velocity across this damper. Right? So the spring and damper undergo different displacements. And we want to measure those. So we'll define 3 coordinates ultimately here, and those will be related by constraint equations. So in addition, we said that when the bar is horizontal, the system is in static equilibrium. And that allows us to neglect the role of gravity here when, again, we measure from static equilibrium. Now, I'd like to contrast that just with a thought experiment to an earlier problem that we did where we had a bar that was hanging down. In that case, we couldn't neglect gravity, right? Because the bar provided, well, gravity provided a restoring moment on the bar. So the moment produced by gravity was not constant. However, in this case, because the bar is horizontal in the static equilibrium position, then when we linearize, we'll find that the moment produced by that force is also constant. So again, constant forces, constant moments, right, and constant forcing for the equations of motion can be eliminated when measured from static equilibrium. So let's look at those forces again. So the forces, and again, neglecting gravity, arise from the reaction at the pin. So here we will define that force as R. Again, it's the reaction force. Then we have a force due to the spring, and that we'll define as Fs. Finally, we have a force due to the damper. And for that, we will define it as Fd. Once again, we have three forces. The reaction force acts at point O. The force on the spring will say acts at point A. The damper acts at point B. And then finally, we'll denote the end of the bar where the disc is rigidly welded as point C. The next step is coordinates and directions. So we want to identify directions that are important to this system. Those are going to be I and J. Right, so I and J here will be fixed in the ground. Put those over here. And horizontal and vertical. And then, of course, we have directions that are associated with the bar itself. Right, so we'll define those as E1 and E2. So again, I and J are fixed in the ground. And E1, E2 are fixed in the bar, or the object, beta. So, with those directions, what coordinates should we identify? Well, let's first look at the motion. This bar rotates, so it totally makes sense to identify the rotation of this bar with an angle theta. Now, when we look at the forces, the force in the spring will depend on the displacement of the spring as measured from static equilibrium. When the bar is horizontal, we're in static equilibrium, so we'll measure basically the location of point A relative to the ground. Let's call that Z. The damper, well, that depends on the velocity across the damper, right? So we'll measure the change in length of the damper with Y. So it is important here to remember that each coordinate vanishes in static equilibrium. So when the bar is horizontal, then theta is equal to 0, and Z is equal to 0, and Y is equal to 0. That'll make it easy to relate these coordinates one to another. Which, let's look at that now. So, kinematics, right? What's the motion? Well, for small displacements, we can relate the coordinates and directions and determine the acceleration or the angular acceleration of this bar. So with this, we see that E1, for example, this direction along the bar, in general is cosine of theta in the I direction and sine of theta in the J direction. And E2 is minus sine of theta in the I direction and cosine of theta in the J direction. But again, small displacements, sine of theta is approximately theta, and cosine of theta is approximately 1. So as a result, we're just going to keep the lowest order term here, right? So E1 here is approximately I. E2 is basically in the J direction, right? So for the directions, we'll only keep kind of the dominant directions. Now, in terms of these coordinates, we can identify the angular acceleration of the bar as theta double dot in the k direction. Right, theta measures the rotation, so theta dot would be the angular velocity, and theta double dot is the angular acceleration. Now finally, I'd like to relate these different coordinates. So to do that, I'll look at the velocity of A and then the velocity of B. All right, so here the velocity of A is the velocity of O plus the angular velocity cross R of A with respect to O. Okay, well, what is that? Here, the velocity of A can be directly written in terms of Z. Right, so this is Z dot in the J direction. Now, the velocity of O is 0, because O is pinned to the ground. This becomes theta dot K, that's the angular velocity, and then A with respect to O, well, that's L over 3 in the E1 direction. Although, remember that E1 was basically I, so K across I is J, and this becomes L theta dot over 3 in the J direction. So we can relate Z dot and theta dot in this way. So let's do the same for B. Well, the velocity of B, again, the velocity of O plus the angular velocity cross the position of B with respect to O. So that's going to be theta dot in the K direction, and then 2L over 3 in the E1 direction. Well, you know, everything kind of follows as before. The velocity of B here is naturally written in terms of Y, as Y dot in the J direction. And again, for small displacements, E1 is basically I, so K cross I is equal to J, and we get 2L over 3 theta dot in the J direction. Right, so here, Z dot is equal to L over 3 times theta dot, and we find that Y dot is equal to 2L over 3 times theta dot. Once again, this is for small displacements, right? But we're interested in the linearization of this problem, so this all works out. Now, let's look at the forces that act on this object. And we want to write these in terms of the coordinates and directions that we identified previously. So let's look at the spring force first. Here, Z was the stretch in the spring. So this force, when I write it in terms of Z, is going to be minus K times Z in the J direction. The damping force here is minus B times Y dot in the J direction. Again, if Y is positive, and if Y dot is positive, this point B is moving up, so that if Y dot is positive, the force from the damper is actually down, right? And that's what we have here. If Y dot was negative, then point B would be moving down, right? And then the force would be directed up. Well, if Y dot is negative, then this term is in the plus J direction. Finally, we have the reaction force acting at O. I don't know anything at all about that, right? So I'll just say it's Rx in the I direction and Ry in the J direction. So I'm just identifying the components in the I and J direction specifically. I'd like to remind you here that because we're measuring from static equilibrium, right, we don't have to include gravity in the response of this system. So next is equations of motion. And here we will apply angular momentum balance about point O. When we do that, we eliminate the reaction force because the reaction force acts at O, so it produces no moment. Okay, sum of the moments about O is the moment of inertia about O of the object times the angular acceleration of the object. I'll remind you that the moment about, say, a point A from a force acting at P is the position of P with respect to A cross F acting at P. Just to remind you again, the definition of a moment and how we calculate that. Looking at our free body diagram, the reaction force, again, produces no moment. Then let's calculate the moment produced by the spring, right? So that's moment arm, R of A with respect to O. Here, L over 3 in the E1 direction, cross the force itself, so that's minus K times Z in the J direction. Then we have the moment produced by the damper. Moment arm here is, or the R of B with respect to O, 2L over 3 in the E1 direction, cross the force itself, minus B, Y dot in the J direction. And that's going to be equal to the moment of inertia of this object about point O times the angular acceleration, which we already said was theta double dot in the K direction. Once again, E1 is basically I, E2 is basically J. Again, this linearized view of things, right? So I cross J, that's equal to K. So we have KL over 3 minus Z, and I'll factor out the direction in a second. I cross J is again equal to K, so that's minus 2B times L over 3 Y dot, both of those are in the K direction, is equal to the moment of inertia times theta double dot in the K direction. So we need to talk about the moment of inertia for this composite object. Anytime I have a composite object, basically it's going to be the moment of inertia of the two parts. So the bar about O plus the disk about O. Well, we know the moment of inertia of a bar about the end. Although we could use the parallel axis to derive that, right? It is a fairly common thing, so I'll just take that directly. But now this moment of inertia of the disk, I will use the parallel axis theorem to figure that out. It's the moment of inertia of the disk about its center of mass. Well, its center of mass is located at C, plus the mass of the disk times the distance between C and O squared. Putting all this in, again, moment of inertia of a bar is ml squared over 3. And again, that's about the end. If this was the center, right, it would be ml squared over 12. And then here, the moment of inertia of a disk is m times the radius squared divided by 2, plus the mass of the disk, again, that's m2, and the distance from C to O is just the length of the bar. So that's L squared. And we're ready to proceed. We have the moment of inertia of this composite object, which will go right in here. Right? We have angular momentum balance applied. And from our previous work with the kinematics, we can relate Z and Y and theta. So here it is again, right? This was angular momentum balance that I've just rewritten from the previous slide. And then these are my coordinate relations that I developed when I was talking about the kinematics. So let's just combine all this. And let's write this in terms of the angle of rotation, theta. So we have m1L squared over 3 plus m2R squared over 2. So this is just the moment of inertia times theta double dot. And then we'll bring these to the other side and use our coordinate relationships. So let's do the velocity first. that becomes 4bl squared over 9, right? 3 times 3 here, because we have to take this y dot and put it into this expression, times theta dot. And then we'll do the same for z. Notice that this constraint relationship is given in terms of the velocities, but if I integrate with respect to time, z is equal to L over 3 times theta. And so that gives me KL squared over 9 times theta equals 0. Okay, I can simplify this a little bit. Notice that there's a bunch of L squares that I can cancel out. I got a factor of 3 that's common here. So, in fact, I can rewrite this with just a little bit of algebra as m1 plus 3m2 and then 1. Here I've factored out an L squared from all these terms, so I pick up 1 in the denominator. Theta double dot. This piece, the damping coefficient is 4b over 3, and then the stiffness coefficient here is k over 3 times theta is equal to 0. And if we go back and look at the original problem statement, I wanted to know the linearized equations of motion, as well as the equivalent mass, damping, and stiffness. So this is the linearized equation of motion. It's valid for small angles, and in this problem, that really implies that sine of theta is approximately theta, and cosine of theta is approximately 1. Then, the equivalent mass we identify as this term in front of the theta double dot. All right, so it's m1, 3m2 times 1 plus r squared over 2l squared. The equivalent damping here is 4b over 3, and of course the equivalent stiffness is k over 3. So there we have the equation of motion as well as the equivalent parameters. Now, just a little bit more. Notice that if r goes to 0, so the radius of this disk were to shrink in such a way that the mass stayed constant, then the disk becomes a point mass. Right, so remember, a point mass is a mass with 0 size but finite mass. So in that case, setting r equal to 0, we might find that the natural frequency is, well, just like always, equivalent stiffness divided by equivalent mass. And so in this case, right, we can simplify this. A little bit of algebra. We get 3 times m1 plus 3m2. Notice that in this case, this term drops out. The damping ratio, again, equivalent damping, 2 square root equivalent stiffness times equivalent mass. And so we can write this, a little bit of algebra again, square root 3k times m1 plus 3m2. So here we see the effect of the size of the disk. And what happens if it becomes, essentially 0 size? So just adding a lump of mass out here. To finish this off, I'd like to talk a little bit more about neglecting gravity and kind of why we can do that in this problem. So to start off with, we need to talk about, right, the weight of this object. And here, the weight of the object, and that becomes m1 plus m2 times g, because the total mass of this object is the mass of the bar plus the mass of the disk, and it acts at the mass center. where is the mass center? Well, that needs to be determined. We can determine where the mass center is by using our, well, basically the definition of the mass center. So that's the total mass of the system times the position of G with respect to some point. And here, let's use point O, as we see here. So let's measure the mass center with respect to O. And we'll identify that point as G. And that's going to be basically the mass of the individual parts times the location of their mass center. So here we have the mass of the bar times the position of the center of the bar with respect to O. So let's call the center of the bar right there at D. And then the mass of the disk times the position of its mass center, which is C, again with respect to O. Well, I can go and figure out all of these things. Total mass is M1 plus M2. The position of G with respect to O, it's some unknown distance D, and D is what we're looking for. We want to know where this thing is. It's in the E1 direction. The position of the mass center of the bar, that's just half the length, again, in the E1 direction. And then the position of the disk, location of its mass center is at the end of the bar. So, solving this equation, we find that D is, well, we can write it as M1 plus 2M2 divided by 2 times M1 plus M2 times the length of the bar. Right? This M1 plus M2 comes from here, and then what's left? Well, we have the M1 over 2 times L, and then M2 times L from there. Right? So I can basically determine where this mass center is. And so let's put that point, let's define that point right there. And let's see that. Let's say that's where it is. So now let's look at the spring force as measured from the unstretched position of the spring. Right? So here in this picture, basically I have this spring, and in its unstretched position, maybe it has a length of L. Okay, so let's measure then the stretch in the spring. Well, the static equilibrium stretch is XQ. And then let's identify the stretch in the spring, or actually the compression in the spring, as measured from the unstretched length as X. Again, here, X is the compression of the spring from the unstretched position, or the unstretched length. As a result, we can relate X and our coordinate Z that we used earlier together with this equilibrium stretch. Right? So X here is X equilibrium minus Z. As a result, when we again go and look at the forces, well, once again, I've got a reaction force. I don't know anything at all about that. I have a spring force. And now I'll choose to write that in terms of X. Right, so it's K times X in the J direction. If X is positive, this force is up. And then I have the weight. And that's minus M1 plus M2 G in the J direction. So with that, I will look at the moments. Some of the moments about point O. Well, once again, moments are R cross F. Right? So I get L over 3 in the E1 direction cross the force here. Right? So that's going to be K times X. Well, I'll go ahead and write x as x equilibrium minus z. And that's in the j direction. Here, I'm just going to look at the balance between the force due to the spring and the force due to gravity, right? So in general, there would be a moment due to the damper here, right? But I'm just going to focus on these two and how these balance out. So then the moment due to gravity is d in the E1 direction cross the weight, m1 plus m2 g in the j direction. Recall that E1 is cosine of theta I plus sine of theta j. Because I want to include the trigonometry here, and then I'll show how that drops out when we linearize. This moment reduces to the following. E1 cross j, well, that's going to be I cross j, which is equal to k. Right, so I have k L over 3 x equilibrium minus z times cosine of theta. Right, and that's all going to be in the k direction. Likewise, here I have E1 cross j. Again, that's going to be cosine of theta in the k direction. So we get minus d m1 plus m2 g cosine of theta in the k direction. So when we have static equilibrium, these two balance out, right? And so in particular, in static equilibrium, z is equal to 0. And so we can find a relationship between, well, actually we can solve for the static equilibrium displacement in the spring. So that gives me x equilibrium as 3 times d was given up here, m1 plus m2 times g divided by k times L. Notice that each one of these terms has a cosine of theta, and so that cancels out. Well, going back to what would happen in the dynamic case with z non-zero, if I assume that this is the static equilibrium position, or if I solve for this in particular, then the moments produced here become minus k L z divided by 3. And notice that this term and this term have been chosen so that they cancel each other out. So I just get minus kl times z over 3 times cosine of theta in the k direction. And again, since we're dealing with a linearized problem, cosine of theta is approximately 1. And so this reduces to minus kl over 3 times z in the k direction, which is what we had when we neglected gravity, right? This term is just minus kl over 3 times z. So in this case, the moment produced from the weight balances out the moment produced by the static displacement of the spring. Right? So since those two things cancel out of the equations of motion, it's equivalent to considering the system with no gravity and no unstretched length of the spring. So again, we're able to neglect both of those effects, but only when the system is horizontal in its static equilibrium position. Right, so that's it for this problem. Again, let's go back and look at what we did. We have a composite object, and we've done two things that are really unique to this lecture. Right, one of them is that we've looked at how to deal with composite objects, and we've done that through the moment of inertia about, say, the endpoint in this case. Right, so if ever you have one of these composite objects, right, you're going to probably need to find the moment of inertia about some other point. And then the second kind of unique aspect of this problem is that we're looking at a bar that's horizontal in its static equilibrium displacement, and we've shown how that leads to equations of motion that are independent of the weight of the bar and the effect of gravity. So when we measure from static equilibrium, we can effectively neglect gravity in the response. I will remind you that this is only true when the bar is horizontal in its static equilibrium position. As we saw in a previous lecture, if it's hanging straight up and down, or if its static equilibrium is vertical, then we absolutely cannot neglect gravity, right? So the question of whether we can and cannot neglect gravity really depends on the system that we're looking at. So that's it. Thanks a lot. As always, I welcome any questions or comments, right? If you have any feedback on this, please send me an email, right? Leave a comment. Let me know what you think. Thanks a lot, and I'll talk to you again. Take care. Bye.